Hello Year 13, right, last little bit on integration now, last skill you need to learn. We've got probably 2 more lessons on this at most, okay? So, last bit, differential equations. Now this leads on really nicely from relating rates of change that you did yesterday. Differential equations, links yx and dydx together. You're going to get them appear in the same equation, okay? And we've got to be able to solve them. And in order to solve them, we need to basically get rid of the dydx. Okay, so if we look at the first one, so we've got dydx equals xy plus y. First thing you've always got to do is to get y to the side of dydx. Okay, now in order to do that, we have to use division, and that's the really important bit to start with. You have to divide to get it. It's no good adding and subtracting. You've got to divide. Now, quite a lot of the time that will mean factorising out. That's absolutely fine. Quite a lot of the time that's what it means. So we factorise out our y or our x and we manoeuvre from there. So to get y to the other side. So if we're starting with dy dx equaling xy plus y, in order to get y to the side, I'm going to need to factorise y out. So all I'm going to do is take out the power of y, so I'll have x plus 1 there, and I'm going to divide y underneath. So what I'll end up with is 1 over y dy dx, because I divided y under, equals x plus 1. So all of my y's are on the side of dy dx, everything on the other side is x's. Okay. Next step is to integrate both sides with respect to x. Okay. So what we end up with is we end up with the integral of 1 over y dy dx equals the integral of x plus 1 dx. Now, the reason this works really nicely for us is because these two dx's cancel each other out, a bit like with the chain rule. Okay, so what I've actually got on the left-hand side is I'm integrating 1 over y with respect to y. On the right-hand side, I'm integrating x plus 1 with respect to x. So integrating gets rid of them all. Okay, so I can integrate both parts. So if I integrate 1 over y with respect to y, I'm going to get log natural y equals the integral of x plus 1 will give me x squared over 2 plus x, nice and easy on the right hand side. But again, you've got to make sure you remember to add somewhere in our constant. Easier to put it in sooner rather than later. We can always manipulate it to what we need to because it is just any unknown we want. The last part you need to do is make y the subject, obviously only if the question asks you to. Sometimes they're happy for you to leave it like that, or they'll ask you to leave it in a different form. If I want to make y the subject, obviously I need to get rid of the log natural. To get rid of the log natural, use the inverse, which is to e both sides. So I'll end up with y equals e to the power of x squared over 2 plus x plus c. Now, it's a common thing with these when we've got e's involved, okay, we don't want to leave it like this because the constant we don't want to leave in that form. And this will link into the bit that you're going to do next week on where we use differential equations a little bit more. What I'm just going to do, and it's the case of what we normally do, and you'll be asked to write it in this form, is we're just going to separate out that last bit with the constant. And I'm just going to write it like that because we know when we multiply, we're going to add the powers together. And all we do is we change e to the c, and the letter we tend to use is a. So it just becomes a lots of e to the x squared over 2 plus x. So all I've done is changed my e to the c to an a, and that's all that's changed. And potentially just to tidy it up a little bit, we get rid of the multiply sign. So I'll have a e to the x squared over 2 plus x. Okay, very similar to what we did with our logs and exponentials topic last year. Just to tidy it up, that tends to be the form if you're working with e's and log naturals that they want it in. Okay, and that's the general solution. Okay, so general solution means getting it into the form of y equals something unless it tells you otherwise. 3 steps in order to get there. We get y to one side of the equation with the dy dx by dividing and probably by factorising. Integrate both sides with respect to x, and it's the fact that they cancel out. Okay, integrate both and just rearrange. Now, you don't necessarily need to write in the dx's that are crossed out each time, so these parts you won't necessarily always write in. Sometimes it's just easier just to go straight to, I know it cancels out, so we just leave it from there. Okay, right, let's have a look at another one. So, find the general solution to 1 plus x squared dy dx equals x tan y. Okay, so what we've got, we need to get the y's to the side with dy dx and everything else to the other side. So just a little bit of rearranging more than anything. So I'm going to divide both sides by tan y and also divide both sides by 1 plus x squared. I'm going to do that at the same time. So what I'm going to end up with is 1 over tan y dy dx equals x over 1 plus x squared. So I've divided both sides by tan y and then divided both sides by 1 plus x squared. So effectively they've just divided underneath. Okay, just done it in one step a little bit quicker. Now I've got both sides how I want them set up. I can integrate. What I do just want to do first, I don't want to integrate 1 over tan y. I know 1 over tan y actually equals cot y. And I can integrate cot y a lot easier. Okay, so what we're actually going to do is we're going to integrate cot y instead. So this becomes the integral of cot y dy, because actually we'll put that in, dy dx, and obviously those dx's will cancel, equals the integral of x over 1 plus x squared with respect to x. Integral of cot y comes out of our formula book, so we can integrate cot y quite happily. Integrating cot y takes us to log natural sine y. Okay, that should come out straight of the formula book. Right, integrating x over 1 plus x squared. I'm hoping you recognise relatively quickly that this is a version of the chain rule. Okay, we can use the reverse chain rule to help us work this out. Okay, where we guess it's going to be something and then we manipulate it at the end. Because I've got a fraction and the top of my fraction is very similar to the differential of the bottom. It's just going to be a scalar out. That's what I'm going to use. So take that into the gap. So I'm presuming because it's a fraction and the top and the numerator is roughly the differential of the denominator, it's got to be log natural. So my guess is it's going to be y equals log natural 1 plus x squared. Okay, so u equals 1 plus x squared, y equals log natural u. So dy du is going to equal 1 over u. Du dx will equal 2x. So dy dx will equal 2x over 1 plus x squared. In order to get that back to what I want, all I need to do is times it by a half. Okay, because that'll take me back to x over 1 plus x squared. So it's what I guessed, combined with my scalar, and that's my integral. So we'll have equals a half log natural 1 plus x squared. Again, we need our plus c. If you cannot remember doing that, guys, you need to go back and look at the reverse chain rule video, okay, that I set you a few weeks ago. Really important we can combine all of these parts together now into one type of question. We've kept building on what we've done before. Now, once we're in this position, if everything is in terms of log naturals, okay, especially the right-hand side, if the right-hand side is in terms of log naturals, I don't want plus c anymore as my constant of integration, okay? What I'm going to do is I'm going to let c equal log natural k instead. Just means I can simplify everything together that little bit easier. So this actually becomes log natural of sine y equals half log natural 1 plus x squared plus log natural k. Okay. Now I do that because what that now means is I can combine lots of this together. Okay, right. I need to simplify my log naturals. So first thing I need to get rid of is I'll get rid of my half in front. If I've got a half multiplied by my log natural, I know I can change that to be a power. So that's going to end up being log natural 1 plus x squared to the power of a half plus log natural k. And then I know when I add with log naturals, I can multiply the log naturals together. So it's going to be log natural k lots of 1 plus x squared to the power of a half. And what we'll actually do is, rather than using the power of a half, we can change that to k root 1 plus x squared. Okay, so all we've done is we simplified that down. This still equals log natural sine y. So all we're trying to do now is work it all the way down so I can make y the subject. Can now get rid of the log naturals. I can e both sides, and that will give me sine y equals k root 1 plus x squared. Finally, to make it y, I'm going to inverse sine both sides, but when we're using this, we don't tend to use sine to the minus 1. We're going to use arc sine instead. So it's arc sine lots of k 1 plus x squared. A little bit of difficult manipulation there to get to the final point, okay, but it's exactly the same idea. All we're doing, get y onto one side with the dy dx, integrate both sides. The left ends up integrating with respect to y because the dx cancel. We integrate the right with respect to x. If we've got log naturals on the right hand side, okay, we look at changing that c to log natural k. Use your laws of logs to combine it all together, and then just manipulate it so it is y equals something instead. Okay, right. So, next step with this. So, what we've now got is we've got find the general solution, and then we've got given that x equals 1 when y equals 4, leave your answer in the form of y equals f of x. Okay, so what that will do is that will get rid of our plus c or our a in front of our e to the something or our k's or something like that. It will just give us everything in terms of y and x. So we've got something to sub into at the end. Okay, right. What we've got in front of us. So we have find general solution to y dx of minus 3 lots of y minus 2 over 2x plus 1 x plus 2. Now I'm hoping you see this and straight away we think about, right, I'm going to have to use partial fractions to integrate. Okay, I've got a fraction, I've got a product on the bottom. In order to integrate it, I'm going to have to use partial fractions somewhere along the line. Okay, right, first step is always going to be the same. We've got to get y on one side, everything else on the other. Okay, so all I'm going to do is I'm going to divide by y minus 2 on both sides. Okay, so the first thing I'm going to do, just get put up here just to make it a little bit easier, I'm going to divide by y minus 2. So take that underneath. So what I'll be left with is 1 over y minus 2 dy dx equals minus 3 over 2x plus 1 x plus 2. Okay, so all I've done, taken that out, divided both sides by y minus 2, and we get to the point of having y on the side of dy dx and everything else on the other. Now I'm going to have to integrate. So integrate both sides. The right hand side with respect to x, obviously the left hand side will be with respect to x, but the dx's cancel out, so we're with respect to y. 1 over y to the y minus 2 is nice and simple. That one's going to go to log natural y minus 2. Slightly more difficult the right hand side, we're going to have to use partial fractions. So first thing you're going to need to do, same as what we did earlier on in the topic, we'll take that and we've got to work out, using the partial fractions, what the split of the fraction is. Okay, So what we end up with is we're going to end up with minus 3 equals a lots of x plus 2 plus b lots of 2x plus 1. So set up your partial fractions, guys, and then we'll manipulate it round. Okay, we're going to need values to sub in. So first one, if I make x equal minus 2, then we're going to have minus 3 equals the a's cancel, equals minus 3b. Therefore, b is going to equal 1. Okay, and then we're going to have x equaling minus a half. So we'll have minus 3 equals 3 over 2a. So a will end up equaling negative 2. Okay. What I am hoping you've put in above is the fact that what we've actually got is we had a over 2x plus 1 plus b over x plus 2. Okay, that would have been a better line to write in, and then we go down to this. So we can then put the two parts back in, put I and b back in, and that's what we're going to integrate. So it's going to be minus 2 over 2x plus 1 and 1 over x plus 2. I'm just going to swap the order around so we keep the negative second. So we've got 1 over x plus 2, so I've just put b first. Subtract 2 over 2x plus 1. And that still needs to be integrated with respect to x. Okay, now we can integrate. So we've got log natural y minus 2 equals, first bit nice and simple, log natural x plus 2. Second bit slightly harder because it's going to be 2 log natural 2x plus 1. But what we have to remember, okay, is the fact that because we've got a coefficient of x inside my log natural, I need to counterbalance it by doing 1 over that coefficient, so times by a half. And again, we're going to plus c. Again, guys, if this bit here you can't remember doing, you need to go back and look at where we integrated f of ax plus b right at the start of this topic. Okay, it's all about that counterbalancing by timesing by 1 over that coefficient of x. Okay, really important that we keep bringing this old knowledge back. Simplify that all together. So I'll have log natural y minus 2 equals log natural x plus 2. The half and the 2 will cancel out. So I end up with minus log natural of 2x plus 1. Because I'm in terms of log natural, I'm going to change my c to the log natural k. Okay. Simplify our right-hand side using our log laws. So we'll have log natural y minus 2 equals, well, the plus k can combine with the x plus 2. So we'll have log natural of k lots of x plus 2 because they can be multiplied. Then we're subtracting 2x minus 1, so that can be divided underneath, just using our log laws again. Okay, right. Log naturals on both sides, counterbalance them. E both sides gives us y minus 2 equals k lots of x plus 2 over 2x plus 1. Now this is where we would finish for the last one, or we might add the 2 to both sides. This time, where it's different is we can work out k. Because we are given at the top general values for x and y, we can work out what k is. So when x equals 1 and y equals 4, that's going to give me 2 equals, so subbing the y in. When x is 1, we end up with 3k over 4. Therefore, 3k over 3 even. Therefore, k must equal 2. So we can sub this back in. So we have y minus 2 equals, subbing that into the top, gives me 2x plus 4 over 2x plus 1. I can just manoeuvre that across, and we can change it, and we can manipulate it around, and we can have y equals 2x plus 2. Sorry, 2x plus 4 over 2x plus 1. Add on 2. What you can do, when we're at this point, we can simplify a little bit further. If needed to, we could use partial fractions to simplify it. I'm more than happy for us to leave it at that point. You got to be really careful with these, guys. It's going to be using all of your integral knowledge that you've built on so far into the form of one question. Okay, so for example, this one used integrating partial fractions, integrating fractions to make log naturals, counterbalancing when we're doing integrating f of ax plus b. So we've got to counterbalance with the 1 over a. Then we're subbing in and we're rearranging. Lots and lots of knowledge in here. It can be really tough stuff, okay? Make sure you're going back and rewatching other videos if you need to, just to recap on what you've done. Right. What I want you to do, I want you to pause the video now. I want you to have a go at this one for me, okay, and see what we can do. My advice would be, once you've got y on one side, we do not want to integrate something over cos squared. You want to change that using one of your trig identities to something else that we can integrate using the formula book. Okay, so 1 over cos squared equals something, and then we can integrate that, and then you can work your way through. Again, same as the last one, you are given values of y and x to sub in to find out what c is at the end. So pause the video and have a go for me, please. Okay, guys, right, let's have a look then. So, very similar setup to the last one in terms of what we're going to have to do at the end. A little bit easier integrating though. So, y's got to be on one side. So we're going to multiply both sides by y. So what we end up with is y dy dx equals 3 over cos squared x. I'm now in the position to integrate. So I can integrate y. That's going to end up being with respect to y because the dx's will cancel. Equals the integral of 3 over cos squared x. Now I don't want to integrate 3 over cos squared x. So I'm just going to change this to, instead it's going to be the integral of 3 sec squared x. Okay, because sec squared I know I can integrate because that is in the formula book. Okay, so the integral of 3 sec squared x with respect to x gives me 3 tan x. So where you've got to make sure you use your formula books, guys. So I'm going to make sure I've integrated both sides now. So y will integrate to y squared over 2. Do not make a mistake with your easy integrating. If it's just a term on its own, guys, back to year 12 and we can definitely integrate those. Equals 3 tan x, because we integrate it as sec squared instead, plus c. Not in terms of log naturals at all, so we're not going to make it log natural k. Not in terms of e's, so we haven't got to make it ae to the something. Just exactly like that for now. We're now going to sub in our values. So when y equals 2 and x equals pi over 4. When y equals 2, we end up with 2 equaling tan of pi over 4 will give us an answer of 1. So we end up with 3 plus c. So it means c must equal minus 1. So we can rewrite this as y squared over 2 equals 3 tan x subtract 1. That is solving the differential equation. Okay, you don't need to go any further than that. It's y in terms of x. That's absolutely fine. Sometimes you may be asked to take it a step further, so they may ask you to write it as y equals something. They just ask you to solve the differential equation. You can stop at this point here. It's y's in terms of x's. Okay, right, can you go back on to show my homework for me? Have a go at the questions I've asked you to please get in contact if you need some extra help.